All right, worksheet 29. So we're going to begin talking about the definite integral and some summations and Riemann sums and all that good stuff. Okay, so we're going to do so by looking at the exercises in the worksheet and problems that are similar. First of all, as always, I need to get control of my computer. Okay, here we're going to start by talking about summations, and I want to show you the anatomy of a summation. This part here is just the Greek letter S, Greek capital letter S. And we use it because the word sum starts with the letter S. Really profound there. Then next to the right of this we have an expression which is a function of some variable. In this case, it's a function of your independent variable, and that's the same independent variable that is listed over here, okay, before the equal sign. Has to be a function of that. And then what we have is the starting point of your independent variable, the start value, and you count by ones, and your end value, you include both the start value and the end value. So if you're used to computer science, this may be a surprise to you. If you've never programmed a computer, this will seem obvious. Okay, so sometimes a little knowledge is a dangerous thing. Okay, so think of it as like, just for fun, I'm going to turn everything back to x's. X is 5, 6, 7, 8, 9. And I'm going to sort of tear this apart and say, okay, let's use function notation because you might be more comfortable with it. F of x equals x squared minus 1. Then what is f if we know x? F again is x squared minus 1. So just go ahead and fill that in, and pause the video, fill that in. Okay, so there, filled in the table. Now the next step, which is the last step, is to simply take and add up all these things. So go ahead and do that. Add those up and see what you get. Okay, so by my calculations at 250, let me know if you think that's wrong, but that's what I got. Okay, so the idea is you add up all these guys and that's the answer. So that means this whole summation symbol that you have sitting there has a value of 250. Okay, let me give you another one for practice. Okay, I figured I may as well let the index be x just because I was making f of x, so make your life a little easier. And these parentheses are not necessary, but sometimes they're helpful just to clarify. It depends on the context that you're in. So if you're wondering, you can always put the parentheses in. Okay, so go ahead and figure that out and come back. Okay, so if you look at the values 4, 5, and 6 at the function x plus 3, then you get the values 7, 8, and 9. You add them up, you get 24. Pretty easy, right? So this is equal to 24. While you've got your thinking cap on, let's do something similar. Okay, now what do you think this is? Go ahead and do that one and come back. Okay, hopefully you just said 24 immediately, because what's happening is under the hood, these are the same problems. And so one thing that students sometimes have trouble with is how do you shift these to get two identical problems? It's pretty easy when you have two identical problems sitting there to say, oh yeah, wait, I did them both and it was really the same thing. The reason why people get confused is the same reason people get confused when they're plotting functions. Like here's a function f, and here's the function, let me see. The difference between f of x and f of x minus 2 is that f of x minus 2 moves to the right because it's late by 2 time units. And it's the same issue that people have with summation symbols, is when you do the shifting on the input side, it goes counterintuitive to what you might think. And so the thing you've got to remember is if you move these indices up 1 unit, you have to shift your whole function down by 1 unit. And so what I did is I shifted these guys down by 3, so I had to shift both of my indices up by 3 because they work in opposite directions. And so just keep in mind that you have to work in opposite directions. If you move them both in the same direction, then you're going to have trouble, right? Because just try it and you'll see why it doesn't work. Okay? So that's something to think about. Okay, and one last exercise to see if you're paying attention. Try to calculate this and then pause the video and come back. Okay, so what this is actually just 40, right? Because what this really means is, let's tear this apart. Here's your x or I, and then f of x equals just 4, right? And how many do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But the function is just 4, 4, 4, 4, 4, 4, 4, 10 copies of the number 4. So your total is just 40. Okay? So it's not that complicated, but you got to keep your wits about you and not overanalyze it, and just sort of take it one step at a time, understand what it means, and just calculate what you're asked to calculate. Okay, next idea, and we need the summation symbol to do this. We have the right and left Riemann sums. So you have some kind of generic function over an interval, and we want to do those rectangles that we've been doing. So you want to go from, say, A to B, and you want to have n rectangles, and you want to go we'll just do the left Riemann sum, but the right Riemann sum is almost identical. So we need to figure out how to actually address these guys. If this is f of x, this is going to be f of a over here. So this point is a, comma of f of a. But what is the very next one going to be? Well, it's going to be a plus the width of the interval, which is b minus a, divided by n, right? And then the next x value is going to be a plus b minus a over n times 2. Okay, so it's going to be the same width but times 2. And then the following, at the very, very end, it's going to be a plus b minus a over n times n, which of course is actually equal to b. So look at that for a while until it makes sense. Pause the video if you have to. Okay, I'm just going to make that picture smaller, and we're going to talk about left Riemann sums. So we're going to actually look at the left side of each of these, and not with any concern about whether we're over or under approximating or sum of each. Now we're going to find the area under the left Riemann sum. Okay? Okay, so for each rectangle, and we have rectangles from 1 to n, we need to know the height and the width of the triangle. We need to know the height and the width of the rectangle. But the width is the same for all of them, so because we're doing Riemann sums, they're constant. What is the width? It's going to be b minus a over n. So we only need the height now. Okay? So what is the height of the first one? Well, the height of the first one is f of a. And the height of the second one is f of a plus b minus a over n. And then the height of the third one is f of a plus 2 times b minus a over n. And finally we get f of a plus n minus 1 times b minus a over n. Because we're doing the left Riemann sum, we actually never arrive at b. So what does this mean for a generic rectangle I? The height is f of a plus, and this is crazy because it's going to be I minus 1 times b minus a over n. And you might say, well, that's really messy, and I agree with you. There's ways to make it easier. We could number the rectangles 0 through n minus 1, and then that makes our lives a lot easier. But for now, I'm not going to do that. Okay? So I'm just going to leave it like that. Then what I'm going to do, I'm just going to make this a little smaller so that we have more space to write. Okay. Now what I'm going to do is I'm going to do a summation. And it's going to be I equals 1 to n b minus a over n, because that's the width of the rectangle, and then the height at the given point. And there you go. That is the left Riemann sum. So how do you think we do the right Riemann sum? Think about it, pause, and see how you change this formula to get the right Riemann sum. Almost identical. So the right Riemann sum is going to have the same width. The only difference is instead of doing the subtract right there, we're just going to squeeze this guy over. If it's unclear to you that that's a multiplication, put that in an additional set of parentheses. Okay? So you just shift everything over to the right one little tiny bit, and you've got the right Riemann sum. So for f of x is x cubed, I would like you to set up the left Riemann sum. You don't have to evaluate it, but just set up the summation symbol. You're going to go from x's 1 to 4 with 12 rectangles. Think about it, and I'll give you points where it's you can stop this along the way if you need help. Okay, so the first thing you want to do is you just want to, in your mind's eye, figure out what this thing is going to look like. And it's going to look like, so there's x cubed, it's going to look kind of like this from 1 to 4. But it's really, really steep, but I'm just going to make it look less steep so that we can draw more rectangles easily. Okay, so obviously it's steeper than that. Here you're going from 1 to 4, 2, 3. Okay, so if we were just to take, if we were to just go by the integers, we get 3 rectangles, but we want 12 rectangles, so we want to subdivide each of these. If we subdivide once, we're just going to get 6 rectangles. I mean, it doesn't always come out so easily, but I did it on purpose to come out easily. So if you want 12 rectangles, b minus a over n is 3 over 12, so it's 1/4. So we're going to call this delta x, and we're going to call it 0.25. So we're just going to give it a separate name so we can refer to it later. Okay, so the width is 0.25. We're going to do a summation symbol, but if there's 12 rectangles, then n is going to be from either 1 to 12 or 0 to 11. I'm going to make it 0 to 11 just because I don't want to have to keep adding 1. You can do it with 1 to 12, it's just going to be a pain. So let's make our 12 rectangles going from 0 to 11. We already have to add 1 as it is. So the width of each rectangle is 0.25, so we've got that covered. And then f is something cubed. So here's our f. All right, now we got to figure out what we're going to do. We're going to say 1 plus 0.25 n, and that's going to mean at n equals 0, we're going to start at 1. When n is 12, we're going to be almost all the way to 4, but since we're doing left Riemann sum, we're never going to get there. But if we were to accidentally put a 12 in here, it's good to just test that, make sure if we make that a 12, it actually reaches the last, the b endpoint. Okay, so you just sort of cheat a little as a test to make sure it reaches. Okay, and who knows what that is? Who cares? The object of the game was to set it up, not to evaluate it. And so that's the object of that game. Okay, now we get to talk about the definite integral in the geometric sense of the word. So we will be talking about this in different ways over the course of the semester, but to get this discussion going, it helps to think about geometry first. Okay, so let's do some functions on some graph paper. And it's easier to start with strictly positive values that are made out of triangles and shapes we recognize. So let's say we have f of x, and let's say this is 0. It could be anything you want. And I'm literally just making this up as I go along. And to do these exercises, first of all, what you want to do is figure out what all the area is and subdivide it into pieces that are easy to break up. And then you can do all the exercises that come. So for example, it's not as easy to split from 0 to 1, but 0 to 2 is really easy, so it's essentially low-lying fruit. Let's do that. So think about it. If this whole area, this whole rectangle, were under the curve, that would be 6. But it's not. It's half of that. So half of 6 is 3. Okay? So one way or another, you figure out that this has an area of 3. All right, the next block that's kind of easy to figure out is this block right here is made up of a triangle and a rectangle. And there's 12 of them here. And again, the triangle is half of the rectangle that it's sitting inside of, so you can tell that there's a total of 2 blocks there. There's 16 here. Why don't you go ahead and subdivide the rest of that? Okay, now we're probably ready to do most any exercise, or at least we're halfway there. Now I'm going to ask you some questions, and I'll answer the first one and then see if you can get it from there. Okay, what is the area under the curve from 2 to 6? And we have to write it this way. Okay, that's a definite integral. That's your first exposure to a definite integral, and we want to know what is the area under the curve from 2 to 6. So we say, aha, the area under the curve from 2 to 6 is a rectangle plus a triangle, so the total is 14. All right, see how this game goes? And by the way, it should not come as a shock that this looks very similar to the summation symbol and all that jazz. This is completely not an accident. And it's not an accident that this thing right here looks like the letter S that's been stretched. Yes, that's exactly what happened to it, and that's where it came from. Very silly, but that's where we got it. Okay, so some things are not all that profound. Some things are just silly. Okay, I'm going to give you some exercises. Okay, pause the video and do these 3. Okay, see, notice that we had to subdivide that rectangle, that we had a square actually that was 16 units, but we had to subdivide it. No big deal, right? Okay, now I'll try giving you a tricky one. Something that I haven't exposed you to. See if you know this. Okay, this is tricky. I want you to notice something. I put these in the wrong order. I put this small number on top and the big number on the bottom. What do you think that does? Okay, so I'm going to tell you, it actually throws in a minus sign because you're running time backwards. Instead of going this way, instead of accumulating, you're accumulating in the negative time direction. So if you want to think of it that way, you're actually going backwards, and that brings in a negative sign. So that's just a rule of thumb, and it will start to make more sense as we do more of these things. But I just wanted to throw that in there for you. Okay, now I'm going to change the f function for you so that it also involves things that are below the axis. Okay, so this function is a combination of semicircles and line segments. And so I would like you to first practice one that should be reasonably easy, which is the integral from 0 to 3, or the area under the curve from 0 to 3, just like that. So just do that, pause the video, figure that out, and come back. Except the fact that I put the equals in the wrong place. Okay, right. So what this is saying is the area under the curve from 0 to 3 is a quarter of a circle, and the circle has radius of 3, so the whole circle is pi r squared, or 9 pi for the whole circle, but we are only looking at a quarter of that circle, and so the area is 9 pi over 4. Okay? You see how this goes? Now, here's the thing. There's another way to get a negative out of this integral symbol, and that's to go below the axis. So think of it as, you save money in the bank account, and that could be positive, and then you spend money, and that's going to go negative. That's one way to think of it. Okay, so just positives and negatives. So you're accumulating debt by going under the axis. So tell me, what is the following if I want to go from 10 to 12? That's going to be negative, but figure out what it is. Okay, did you get minus 2 pi? This is how you should get minus 2 pi. The radius of this circle is 2, so pi r squared is 4 pi. Divided by 2, 4 pi over 2 is 2 pi. So the area of that thing is 2 pi, but because it's underneath the axis, you get a negative sign. All right, and since you already know, if I flip this, I could say, hey, guess what? I can make two negatives make a positive, and you would be correct. So you'd end up with 2 pi. So you're running it backwards, you're getting rid of debt, essentially. And so then you would end up with 2 pi. Okay, let me come up with another one for you. Okay, why don't you try this one? Okay, so this would be 6 minus 2 pi, and actually 2 pi is bigger than 6, so that's actually negative, but it's pretty close to 0. Okay, so hopefully that's enough of those examples. Don't forget that also these examples, you can lift these things up. Like I could have this thing lifted up somewhat, so it can be on top of a rectangle, and that can make it more interesting. Okay, but then you would still subdivide this piece into a semicircle and then a rectangle. So that all works. Oh yes, I wanted to give you a hint. There's nothing on this worksheet that you should have to stress too much over. So if, for example, you see a function that looks like this, something like looks like this, and you don't know what it is, and you're like, oh my gosh, that looks very scary, go to Desmos. This time I'm not going to recommend Desmos or Wolfram Alpha. I'm going to suggest Desmos because I think the graphics are going to lend themselves better on Desmos in this particular case to helping you get out of that jam and figure out what you're looking at. Okay, and that number 5 is a little bit hard, but not really, because I don't want you to overanalyze it. So it's part A, B, C, D, E. So most of those parts are just telling you something that's true, and it really means, so A through D is actually think about. So it's all true statements that says, show that this equals this. So the answer is already there. What you're supposed to show is already sitting there. So basically it means draw some diagrams and convince yourself that that statement is true, and then try to justify it. And this is the perfect thing to do at your tables, is to justify it to the other people at the table so that you're all on the same page and you agree that all those are true and they all make sense. And the only real work is in part E. So if you guys have vetted that and talked through all those explanations with each other and convinced each other that that's all true, then E should not be hard, because E is a direct result of all these things that you've decided are true. And so if you've done the discussion properly, E should be straightforward. And that's it. So I'll see you in class.